Let's talk about some more integration with substitution. We're going to extend that to areas between curves. We've already done areas under a curve. We've done it with Riemann sums. We've done it with, rectangles. We've done it with the integral from 0 to 5, and we've integrated it. We've done it with limit of the sum, limit as n approaches infinity of the sum as k goes to 1 to n of my f of, I'll just call it x sub k times my, basically it was my delta x. We've done all that. But now we're going to do between curves. I'm not really sure why the author called 5-6 the definite integral substitution. And if you remember back, he called 5-5 the indefinite integral, but yet we had definite integral problems in there, at least in the homework. Not so much in the lecture, because the lecture did stick to the indefinite integral, but the homework, you were integrating with some limits. Okay, so I'm going to put a lid on it. Thank you very much. Jump right to it. We're still talking about the substitution formula, better known as integrate u du. But now I'm going to literally talk about what we can do with my limits, a to b. Well, the problem is I shouldn't do a to b right now. Let me do something here. Let me remind you how we came up with that u du. We were first integrating, I'll call this f of f a to b, of f of u. Not even like that. How did we do it before? We did g. We did g of x, g prime of x. And a and b are related to the x's. If I convert this to u du, I have two options, and I'm going to talk about both of them. But theoretically, those limits change as well. The other option is to ignore the limits and convert your f of g of x, g prime of x, which goes from a to b, but ignore it and write out your u du. And don't worry about your limits, and you're going to get some function. You're going to get some function of, I'll call it big F of, well, I'm going to call it big F of x. Well, it's not even x yet. F of u plus c. Then I can convert this back like we did in the other homework. Convert it back into a function of x. And instead of plus c, I now can use my limits from a to b, which were related to the x. I cannot go a to b of the u because I changed my function. So this would not be correct. This would be more or less u of a and u of b. You're changing them in terms of u, not in the terms of the x. So let's see how that works. I like kind of how he kept it with the g and the g prime of a to b, and he actually, well, g was my u, remember? So there's my g of a, there's my g of b, f of u du. So you can actually do that conversion at the very beginning of the problem. And then when you get done integrating and you have this big f of u from g of a to g of b, you can now plug that in and get big F of g of b minus big F of g of a. You can do that, which is probably what he does mostly. I'm going to be honest with you. I'm lazy. I tend to like to just get my antiderivative, my antiderivative, and resubstitute my x's and then do a to b. That works. It works all the time. The only time that plan messes up is on the AP test. There might be a problem where all it is asking you, what are my new limits? So it didn't even matter that you integrated. It mattered, what was my new limits going to be? Really? That was so important to you, Mr. College Board, when you could actually survive without ever doing it? Of course, I don't know everything. There might be a secret. So let's do our first problem. Let's do this both ways to demonstrate. If I'm going to do it the easy way, to me it's the easy way, is to try to find my inner function in here. And my inner function is probably this. And if you think about it, the derivative of x cubed is 3x squared. So it's looking pretty good. So I'm going to let u equal to the x cubed plus 1. Du will be 3x squared dx, which is ironically what I have. So for all practical purposes, I like this lesson because you're reviewing the substitution again. We had 3 lessons in a row you could use substitution. So that turns into, well, I can't put equals because I'm not going to use limits. I'm going to go, I'll save that for last. I'm just going to rewrite this as the integral of u to the 1/2 du, which turns into u to the 3/2 divided by 3/2. And yeah, normally it's a plus c here, and it is. But of course, I'm not going to use that. I'm just going to now do my substitution. My substitution, since I have identified what u is up here, I'm going to plug that x cubed plus 1 back into the u. So I'm looking at 2 times the x cubed plus 1 to the 3/2 over 3, and that's plus c. Now, to make it back into this problem, I can literally, since I've converted this back, I can literally say 2 times x cubed plus 1 to the 3/2 divided by 3, but not plus c, from -1 to 1. Those limits only go with the function after you plug back in the x. Equals to, let's see, if I plug in a 1, it's going to give me 1 cubed plus 1. That's a 2. 2 cubed is 8. Square root 8, well, that's an ugly number. I think everything looks okay. I just wanted it to be a pretty number. So let me plug my 1 again. 1 cubed is 1, plus 1 is 2. So that's a 2/3 times a 2 to the 3/2 power. Plug in the -1. -1 cubed is a -1. -1 plus 1 is 0. That's going to give me 0. So it's minus 0. So I'm going to stick to that answer. 2 times 2 to the 3/2 power divided by 3. And if I'm wrong, just tell me. All right, now that's using the lazy method, if you want to call it that. I'm going to do the problem again with pure substitution all the way, okay? So I'm going to now, I'll rewrite the problem, integrating -1 to 1 of the square root of x cubed plus 1 times 3x squared dx. And basically the u du doesn't change. U is still x cubed plus 1. Du still is 3x squared dx. So now I am going to literally write integrate u to the half du, but this time I am going to find out what my limits have to be. So what we do here is I'm going to use this equation that I created, that u, since these numbers are u numbers, they're not x numbers, they're u numbers. If u is equal to x cubed plus 1, and I'm going to use when x equals to a 1 and an x equals to a -1. So my upper limit when x is a 1, I'm going to plug it into here, I get u will be a 2. So up here, my upper limit changes to a 2. Now, the lower limit, when x is a -1 and I plug it in here, I get a -1 cubed, which is still a -1. -1 plus 1 is 0. So my next one becomes u is equal to 0. That number goes here. You can see they're not the same as -1 and 1, which is why I didn't say it was equal to this with limits. I went and worked it out as indefinite integral here. And then I took that answer and what did I do? I changed it back into the x's right here. And I just worked it out. So let me finish this problem. Hopefully get the same answer. That turns into u to the 3/2 over 3/2 from 0 to 2. Plug in the top number. That's 2 times 2 to the 3/2 over 3 minus 0 equals 2 times 2 to the 3/2 over 3. That's, and it agrees. You see, they agree. So you could choose which one you like doing. Some people love just to do this fast interpretation of the limits. It actually is less work. It is less work. It's just that people don't have time to learn everything. Let's see what the answers were. 4 square root of 2 over 3. 4 square root of 2 over 3. Is that my answer? I had 2 times 2 to the 3/2 over 3. Let's see if his answer is the same. Is that what I had? Hold on. No, I didn't have 2 to the 3/2. Yes, I did. In my problem, that's the same as 2 times 8 to the 1/2 over 3. That's the same. That's equal to 2 times the square root of 8 over 3, which is 2 times the square root of 4 times square root of 2 over 3. That's 2 times 2 square root of 2 over 3. That's 4 square root of 2 over 3. And that's the answer he has here, 4 square root of 2 over 3. I like my answer better because the AP exam does not care. My math lab, on the other hand, he cares. What does he know? Hold on. Try to pick up the pace. I like what he says. Use the method of transforming the limits. He's telling you which way to do it. So I'm going to do it one way. Transform the limits. Let's see. I only got two things here. I got a cotangent and I got a cosecant squared. If u is cotangent of theta, what is the derivative of cotangent? Well, it actually is. Actually, it's not cosecant squared. It's negative cosecant squared theta d theta. So I think I'm just missing my minus. So I put my minus here. Oh, wrong color, wrong pen. Put my minus out front, put my minus out here to balance it out, because a negative times a negative is a positive, it cancels out. So I'm looking at the negative of the integral of a u du. There's my u. My u is the cotangent of theta. It's kind of weird. That's the u. So u du. Gotta fix my limits now. Because it's trig, it tends to be a little more difficult. If u is equal to the cotangent of theta, and the thetas I'm going to use is theta equals to pi over 2, and theta equals to pi over 4. Let me do the upper limit first. Cotangent of pi over 2 will be this u, my first one. Pi over 2 is here. No, that's pi. Pi over 2 is here. There's pi over 2. That ordered pair is 0. Why do I keep grabbing that pen? 0, 1. And cotangent is x over y. And that would be a 0 over 1 is 0. So that limit is 0. So that pi over 2, if I have it right, it's a 0. Let's do the pi over 4. u2 will be the cotangent of pi over 4. Pi over 4 is a 90-degree angle. I'm sorry, what am I saying? 45-degree angle. I'll put it in that quadrant because it looks like it's positive and positive. Could also be negative and negative, so theoretically you could be down here. That would also give you a positive 45-degree, being this is your reference. But let me stick with the principal angle up here. 1 square root of 2. There's my theta of pi over 4. Cotangent is 1. So I get u2 is a 1. And I know a lot of times we're not real comfortable with my smaller number being on top, but it's not wrong. You want to switch them? Then you got to multiply it by a negative. That may not be a bad idea. Why don't we do that? Let's be a rebel. Let's switch the limits to 0 to 1 only because that allows me to multiply this negative 1 by another negative 1, and that turns into positive, so I don't have to worry about it, okay? But I still have my u du now. And as I recall, my u was cotangent of theta, so I'm integrating. Well, actually, what am I doing here? I'm in u substitution. And I'm not going to put it back into cotangent just yet. I'm going to go, when I integrate u, it becomes u squared over 2 from 0 to 1. Plug in the top number, 1/2. Plug in the bottom number, 0, 1/2. That's what I'm sticking with. Let's see. And he left the negative. He left his limits the way they were. But because I was a rebel, he ended up having a minus, and then the 0 was here. So same answer. Potato. Make sure, well, no, you have all. All right, let's do another one. Okay, this is interesting. This was a problem we've done before. We did it as integrate negative pi over 4 to pi over 4. And since I don't know what the derivative of tangent is by memory, because I know the derivative of secant is secant tangent, and the derivative, wait, did I know? The derivative of tangent is secant squared. Yes, I do know the derivative of tangent is secant squared. But I don't want the derivative of tangent. I want the derivative of what is tangent. Derivative of what is tangent? That I don't know. So I did an identity. I wrote that as sine of x over cosine of x dx. And as you recall, well, this became a du over u problem. In other words, I'm going to let u equal to the bottom, cosine of x. Then du would have to be the derivative of cosine, which is a negative sign. So then I'm going to rewrite this problem as the integral of du over u with the negative, because I had to add that negative there, du. Because what I forgot to write was du, well, no, I wrote it, is dx. Negative sine of x dx. I didn't have the negative, so I would have to add it, and I'd have to put it on the outside, which is what happened here. So this became my du. It goes away. That's my du. All right. The simple answer would be negative natural log of the absolute value of u. But I did not do the limits. So let me do that. Let me fix these limits here. What will those limits be? Okay, so more work again. I'll do x equals to negative pi over 4. U is defined as, over here, the cosine of x. So if u is the cosine of x, then what I want to get u, the first one, u1 will be the cosine of a negative pi over 4. Negative, so I need cosine to be negative. That happens in quadrant 2. And a pi over 4, see, I said negative pi over 4, so that tells me that this must be that's a 45-degree angle. 1 square root of 2. And that's negative. Or you could also be in this quadrant as well, because in there my negative 1 is here. But quadrant 2 is your principal angle for, I believe that is for your cosine. We'll find out. So what is the cosine of pi over 4? It's adjacent over hypotenuse, negative 1 over the square root of 2. If I'm doing u2, that would be the cosine of the other one was, I did the negative, I do pi over 4. And that's quadrant 1. They're both positive, and they're both positive down here too, but my primary principal angle is quadrant 1. So that's the one I'll use. 45-degree angle is here. 1, 1, square root of 2. So U2 is 1 over the square root of 2. Both of those I'll rationalize. This turns into the negative square root of, I keep grabbing the wrong pen. Negative square root of 2 over 2. This gives me the positive square root of 2 over 2. So my negative 1 was the one at the bottom. So that was negative square root of 2 over 2. Negative square root of 2 over 2. And my top was square root of 2 over 2. Square root of 2 over 2 gives me the negatives factored out, because I have a negative here. Natural log of square root of 2 over 2, absolute value, minus natural log of the negative square root of 2 over 2, but because when I take the absolute value, I had to turn down my TV, it came on, of the negative number, it becomes positive. So I'm left with equals to a negative natural log. That's already positive, so I'm just going to say square root of 2 over 2 minus, that negative's out front, minus the natural log of square root of 2 over 2. That becomes negative 0 or 0. I'm talking slow because this stuff is heavy stuff, and I did a lot of work in this page. Should you get it all down? Yeah, you really should. Matter of fact, if I didn't show you the whole screen on the other pages, let me, solutions. Let's see if I'm right, and yeah, I'm right. Always gives me goosebumps when I get it right. Let's talk about areas. We've talked about the symmetry before of an even function. That if you start at 0 here and realize that I'm going from negative a to a, and the pictures are identical, that means this area is identical to this area. So since they're both positive areas, you literally don't have to integrate. You do not have to integrate from negative a to a of f of x dx. You could always just do 2 times the integral, where's the middle, 0 to the positive a of f of x dx. That's a theorem, okay? We talked about it. Look at the second picture here. Same thing's happening. Is it or is it not? Let's see. This is, it looks like these two are the same. And this is not an even function. This is an odd function. But it doesn't, the odd function, those 2 places, one's positive, one's negative, they literally cancel out. This is positive and that's negative, they cancel out. So that one's giving you 0. So let's see what the theorems he said. Let f be continuous and on the symmetric interval negative a to a. If a is even, then okay, that's what I just did, even. If f is odd, then the answer is 0. Even meant, let me remind you, because f of c, whatever c I plug in, will be equal to f of the opposite of that c. If I plug in a c of a 1, that gives me a height. if I plug in the opposite of C, gives me the same height. That's the definition of even. Odd is if you have f of C, let me go here, C, gives me a height. If I plug in f of the negative C, f of a negative C, it's the same distance this way, the height is negative. So what happens is they're not the same. They're not equal. It's not equal to f of a negative C. As a matter of fact, f of C is equal to the opposite of f of a negative C, because it was positive and now it's negative. That's also something about an odd function. This function actually has symmetry on the origin as well. Symmetry on the origin means that if I stick a pin here and push this picture and rotate it around, let's say I break it off, I cut this off and I push it, it's gonna turn and it's gonna be upside down. And it's just the same picture if you went around the spinner. I know you wanted to have that. Too far? Okay, here it is. They didn't give me the graph, so this is really cool, guys. You can literally now, I wonder if I can show you. No, I can't show you because I can't get out of the screen. If you go to Google, just go to Google. This is really cool. This is new and improved, which is good that Google's doing something good. You can just type in the word, like in your search box, graph x caret 4 minus 4x caret 2 plus 6. Now it looks like this, x caret 4 minus 4x caret 2 plus 6. And it literally gives you that picture. And you can zoom in and out however you want it to be. So FYI, you got a graphing calculator right there on your Google browser. You don't even need any fancy programs. I did it in Google. I just graphed it, and it graphed it for me. And if I change a number, it'll change it up. Anyway, I'm looking at this function, and it's a fourth degree. So fourth degrees, positive fourth degrees, are always a Whataburger, there it is, or a McDonald's. This is a Whataburger because it's positive. That meant it goes up forever, both sides. Okay? It has symmetry. It's even. Yes, I could integrate from -2 to 2, but I don't have to. It'll work a little faster if I just go from 2 to 2 and times it by 2 and do my 4x to the, no, it wasn't 4x to the fourth, it was just x to the fourth. It's my writing on it that I saw. X to the fourth minus 4x squared plus 6dx. And I don't know why I'm doing this one. You guys can do this yourself. That's 2 times x to the 5 over 5 minus 4x to the 3 over 3 plus 6x over 1 from 0 to 2. Obviously, if I put a 0 in for every one of these terms, it goes away. So the only term I care about, which is why we like symmetry, even functions like that. So that gives me 2 times 32 over 5 minus 4 times 8/3 plus 12. And if I was doing the AP exam, guess what? I'm done. I'm not going to do all that work to add it up. Mr. My Math Lab, though, he thinks he's right, so he wants to. All right, example 3, they did not give us the graph of it in the book. And why do I not have, did I go to finish the work up? And so he's going to make you not only add them up, but write your answer as a fraction. So I would just type it in the calculator exactly as I see it, and then go math, fraction, enter. Just key it in the calculator exactly as you see it, and it'll create that fraction for you. Back to this picture here. What did we find? Stay. -2 to 2. That was the area bounded by that curve. It actually is between two functions, though, because the other function is y equals to 0. And this is between -2 and 2. So it was area between two curves, but the curve was 0. That's why this answer has to be a positive area, because it's above the y equals to 0. I didn't switch. Area between curves, so that's different. Oh, by the way, this picture here, let's study it for a second. There's your top function. Here is your bottom function. And we're talking about the area that is bounded by them both. From A to B. When you are going between two curves, the answer will always be positive area. A lot of times we call the upper curve f of x and we call the lower curve g of x. And you found the area. You literally will always have a positive answer. If f and g are continuous, that's the fancy definition. If f and g are continuous with the f being greater than g throughout the interval, always, the f is on top, then the area of the region bounded by the curves will be f of x, y equals f of x, and y equals g of x from a to b is the integral f minus g. Oh, so you are finding the area under the curve of f, and you're subtracting the area bounded by the curve that's under the axis and f. That would be the area bounded by g. The area bounded by f, I'll put it in red, would be, since my a would be, well, there's a little bit here, and then there's all of this. A little bit of negative, a little bit, and a lot of positive. The area bounded by the axis and the g is all the way up to a, wherever a was at, to the function to the x-axis. If you take the area of f and you subtract the area of g, that explains why it's still going to come out to a positive area, because you're reversing the negative areas. And it really doesn't matter that the axis was in the middle. It happens regardless. The theory behind this is that you make those rectangles like we've done before, and then there's your delta x, and the height of that rectangle is the top minus the bottom. So it's really f of x minus g of x is that height of that rectangle. And how thick is that rectangle? It's a delta x. In terms of calculus, it's from A to B, obviously, because I'm starting at A and then I'm ending at B. So I'm going to do all the limit of the sum of all these rectangles that are in here, all of these rectangles. So let's just integrate f of x instead of adding them all up, and f of x, that's my minus g of x. There's my height. There's my height. Length, or my length, times width, dx. Another problem, same idea. Upper function, lower function. The height of every rectangle is the top function minus the bottom function. That's how the height of that rectangle. And the thickness is always a delta x, always. But in the integral, it's a dx. So we're looking from 0 to 1, apparently. Let's see, from 0 to 1. And you have to identify the top function. So if they don't graph it for you, you wouldn't know. You'd have to graph it first to see which one's on top all the time. It looks like it's 2e to the negative x plus x. Let me make it bigger then so I can get it all in there. 2e to the negative x plus x. Subtract 1/2 e to the negative x. Subtract a 1/2 e to the negative x. That's the setup. Okay. So let's do the work. I'm going to rewrite it here. Integrating from 0 to 1. Top function was e to the, no, it was not e to, it was 2e to the negative x plus x minus e to the x over 2 dx. Let's try to clean this up a little bit. We are doing it by hand. Yes, a calculator could give you the decimal answer. You literally could type that in with your 0 to 1 and just type in this whole ugly mess. Okay, write that out all together as the integral from 0 to 1 of 2e to the negative x plus x minus e to the x over 2 dx. Treat them as 3 different integrals. Integrate. I could do it without doing the u substitution, but I'm just going to demonstrate for you that if you wrote it like this, let me do that first piece. U would be that 2 can go on the outside if you want. I'll just leave it. U would be a negative x. Du would have to be a negative dx. I don't have a negative dx, so I put it negative. There it is. Cancel it out over here. This piece gives me, well, that turns into integrate. Better not do this yet. Let me erase that bracket. Let me go negative integrate a 2 e to the u du. The 2 e to the u, the du, was what I created. That's, the answer is negative 2 e to the u, which is negative 2 e to the negative x. Okay, now that's part of my 3 things here. Back up to the top. Integrate plus integrate x dx. Do I really have to do u substitution for that? Can't you see that is just going to be x squared over 2? So I bring that down, plus the x squared over 2. Oh, that minus was on the just that piece there, yeah. All right, this one here, minus the integral of e to the x. I'll put the half outside this time, dx. Do I have to do e to the u for this problem? Not really. If u is x, then du is dx. It's already there. So that answer is going to be a negative 1/2 e to the x. Bring that down, minus 1/2 e to the x. Each of those three terms I did separately. I'm going from 0 to 1. So that's negative 2 e to the negative 1 plus 1/2 minus e to the 1 is e. That gives me minus e over 2. All of that minus, plug in the 0, e to the 0, or e to the negative 0, is 1. 1 times a negative 2 is negative 2. 0 squared over 2 is 0. E to the 0 is 1. 1 times a half, that gives me a minus a half. This gives me a negative 2 over e plus a half minus e over 2 minus minus 2 plus 2 plus 0 plus a half. To be honest with you, that answer is never going to be pretty. I know this is 2.5 and a 1/2, so I know it's 3 something. And so it's 3 minus whatever these two pieces give me. So you're probably going to pick up a calculator and key it in. So you're going to get a decimal anyway. My warning to you is use 3 decimals. I hope this is right. I mean, there's a lot of little things in here that, why did he have me do this problem? Oh, what was I doing? I was doing the area bounded by these curves. I forgot what I was doing. Anyway, that should be some area. I suspect the answer is positive, based on the picture. Okay, it's all up. Let's see what the solution had. I don't know if I can compare that. Did I have a negative 2e to the negative x? I think so. Did I have a plus half? I think so. Did I have a minus e over 2? I think so. Minus, I think, oh, yeah, there's my 3 I said. 3 and those, yeah, I had this. I feel pretty good. Moving on. The definition. If f and g are continuous, with f always, I did this one already. F is always greater than g throughout the interval, then the area of the region of the curves is going to be integrate f minus g from a to b. This only applies if the one function is constantly above the other function. F is always, it may not always be, because it's possible that they cross here, but maybe my a is here and my b is here, and it doesn't really matter that they cross here. As long as in the interval that I care about. Okay, interesting. Let's study this for a second. Is f constantly above g? If this is my f and this is my g, I'm going from here, -1, to a -2. You put dots, so I'm just guessing. Yes, everywhere you go, f is on top of g. This would be an example where you could do the area is the integral from -1 to 2. The top function is an upside down parabola, 2 minus x squared, put it in parentheses, minus the bottom function is just a line, y equals -x dx. Why don't we finish this problem? We're here. So equals 2. When I integrate 2, that becomes 2x. When I integrate x squared, that becomes minus x cubed over 3. That's a minus minus, that becomes a plus x. That becomes a plus x squared over 2. All of this is going from -1 to 2. Do I have to go any further? I think you can see what's happening. It might even be the next problem. I don't know. Oh, did I do the 3? Oh, there's my x. Yeah, I have the same thing. It is the next problem. Okay. So I hope I said that over there. If you didn't have the picture and you did use your calculator to graph it, you do need to know if you want the total region bounded by these two curves and they don't give you those points, you got to find them. And you can do it with your calculator very easily. You just set both of those equations equal to each other. Where is 2 minus x squared equal to a negative x? You could graph those two functions and tell it to find the intersection of both places. But this is really easy to solve by hand. So let me just say it's I'm going to move everything to the other, everything to the other side. That gives me 2x squared minus x minus 2 equals to 0. Hopefully I can factor this. Well, I know I should because these numbers are very simple. So if I factor this, my method is 2 times a negative 2 is a negative 4. Multiples of numbers that multiply to get a negative 4 that add up to negative 1. Well, a negative 4 and a 1 won't do it. And a negative 1 and a 4 won't do it. A 2 and a negative 2 won't do it. I thought I was going to factor it in. 2 minus x squared equals to a negative x. 2x squared minus x minus 2. Did I write the problem wrong? 2 minus, where did this 2 come from? That's not there. Okay, that makes sense now. X squared minus, okay, that's a 1 instead of a 2, so that's a negative 2 here. Okay, let me fix that. How embarrassing. And you were all watching. And in my head, somebody was yelling at me. How could you be so dumb, Cartwright? I don't know. It's natural. So I moved everything over. All right, so here goes. 1 times a negative 2 is a negative 2. Numbers that multiply to get a negative 2 that add up to negative 1. That's a negative 2 and a 1. Bingo, found it. That means x minus 2 times x plus 1 should be 0. X has to be 2 and x has to be a negative 1, which happens to be my limits. There's the negative 1. There's the 2. So that's, you may have to do that work first because you're not always going to be given a beautiful picture, right? The final, okay, I went by the picture. He is doing something that's very important. Why don't I go back? What if I didn't have the picture? It looks like this is the same thing that I had. 2x plus x squared over 2 minus x cubed over 3. Is that what I had? This is the top function is always above, so I don't know what the problem is. This is the square root function. I see it right here. Square root of x. And this function is a line of x minus 2. Obviously, I'm going from 0 to 4. But let's prove that. Let's set the square root of x equal to, what was that, x minus 2? And that, you guys probably have never done one of these before. It actually is a quadratic. To get a 0 there, you move the square root of x over. That gives you x to the 1 minus x to the half minus 2. This is the same thing as quadratic because a 1 is double the half. So you can just pretend that it's a quadratic. And I'm going to put my, well, it should factor because those are pretty numbers. 1 is there. 1 times a negative 2 is a negative 2. Factors a negative 2 that give me a negative 1. That's a negative 2 and a positive 1 again. But instead of saying x equals 2, I say x to the half equals 2, or minus a 2. And I say x to the half plus 1. And if you FOIL that, I hope it does give me the same thing. X to the half times x to the half is an x. There it is. Negative 2 square roots of x plus square roots of x is a negative 1 square roots of x minus 2. So by doing this, x to the half, or square root of x, equals to 2. Square both sides. X is 4. Square root of x equals to a negative 1. Square both sides. X equals to 1. Did I? 4. Oh, there is a 4 here. They crossed it 4. And x equals to 1. Did I do that one right? It is, but I don't see it. I don't think they crossed it one. I think there's something wrong in my work there. Well, here's the deal. They do cross at the x is 4, but I don't want anything that's, I want to only go from 0 to 4 of the top function, and the bottom function is going from, if it was, let's see, a 2, right? X is 2. So this function is not doing the same interval as this function. So we can, you can't really set it up as one integral. You have to set up as two integrals because this region is sort of independent of that region. They're different. You would only know that if you graphed it and saw it. So you do, I think you always need to look at a graph. Always look and see what's happening. So what I would do with this one, I try to break it up into two major areas. So the top area is one function on top, and it's going from the 0 to the 2. As long as I make sure that's a 2 here. Erase that, make sure I don't mess up. Yeah, that's a 2 here. Then I go on from 2 to the 4. And the 2 to the 4 region has a top function and a bottom function all the way till you get to that ordered pair 4, 2. Okay? So let's try to do this. Okay, I'm going to attempt the impossible. My area will be that first region from 0 to 2 of only x to the half dx. Okay, then I'm going to add to that from 2 to 4 of the top function, which is x to the half, minus the bottom function, which is y equals x minus 2. Okay, and that's not much fun. There's another way of doing this. We can actually do something that's actually cool, but this, I'm going to keep this as 0 to 2 of x to the half dx, plus this one 2 to the 4 x to the half minus x plus the 2 dx. Integrate that first piece, and hopefully I don't mess up. X to the 3 halves divided by 3 halves from 0 to 2, plus this again is an x to the 3 halves divided by 3 halves minus x squared over 2 plus 2x. All of this is going from 2 to 4. From plug in the 2 here, that gives me the square root of 8 again, which was the square root of 4 times square root of 2, which is 2 times 2. That gives me the 4 square roots of 2. We've done this before. Plug in the 0, I get a 0. Plus, all right, I'm going to plug in the 4. Plug in the 4. If I plug in a 4 here, square root of 4 is 2. 2 cubed is 8. 8 times 2 is 16 thirds. Plug in the 4 here. 4 times 4 is 16. 16 over 2 is 8, minus 8. Plug in the 4 here, I get the plus 8. Then I have to subtract, plug in the 2. So it's getting uglier. Again, that's a square root of 8, which is 2 square roots of 2, it's 4. Square roots of 2 over 3. Plug in the 2, that's 4 over 2 minus 2. Plug in the 2, that gives me a plus 4. That gives me a 4 square roots of 2 over 4 plus 16 thirds minus 4 square roots of 2 over 3 plus a 2 minus a 4. 4 square roots of 2 over, that's a 3, over minus that. I'm left with 16 thirds minus 2, which is the same thing as 16 thirds minus 6 thirds. That's 10 thirds. So the area between these two regions is 10 thirds. All right, this is where he actually has us solve the problem. And notice he's obviously telling me to use those vertical rectangles. Picture in the book. What about integrating with respect to the y-axis? Instead of making my vertical rectangles, I could make my horizontal rectangles. In this case, f of x will be like not the top, but the right. And g of x could be my left. It doesn't matter what you call them. But you have a function to the right, to the left. So the height of this rectangle would be the difference between f and g, but it's it's f and g of y's because you had to solve for x. You have to solve both equations for x in order to do this, in order to integrate with respect to y. Nice picture. Same thing happens if you're looking at this lemon. Also, what's going on is you're going from the bottom to the top, so you're integrating the bottom to the top. And the rightmost function, he's calling this right, he's calling it x is f of y. So I'm doing f of y minus g of y. That's the goal. There it is. Bottom to the top, right minus the left function with respect to y. So there's extra work here because you have to solve every equation for x. Notice the same problem we did a minute ago with the answer was 10/3. It's the same picture, but there's an advantage to looking at it this way. I don't have two different pieces to worry about. This might actually be easier, so don't be afraid of it. Let's do it with that way. See, if y equals x plus 2, I got to solve that function for x. So x equals y minus 2. So there is my right function. That's the one on the right. The one on the left, if y equals the square root of x, then I square both sides to get x equals y squared. There's my left function. This time, I don't go from 0 to 4. I'm going to go up because your rectangles are going up. They start down here and your rectangles are going up. So you need to find out what the upper y was, which we did earlier. We know it was a 2. So I'm only going from 0 to 2. So when I set this up, integrate y plus 2 minus y squared from 0 to 2. That's y squared over 2 plus 2y minus y cubed over 3. All of that from 0 to 2. That gives me 2 squared is 4. 4 over 2 is 2. Plus 2 times 2 is 4. Minus 8/3. When I plug in the 0, 0, 0, 0, that all turns to 0. That is 6 minus 8/3. That's 18/3 minus 8/3, and same answer, 10/3. That's the story that I'm sticking with. The answer, 10/3 again. A lot less work to differentiate with respect to y than to x. I like how they did here. This is different, dude. You mean I could have done it another way? I could have done the square root of x from 0 to 2. That line creates an isosceles triangle, 2 by 2. So you could do it. You could do it with the area of that isosceles triangle, 2 by 2. That's a right angle, and the area of that isosceles triangle is base times height divided by 2, which is 2 times 2 1/2 base times height. It gives me a 2. And so instead of dividing it up into 2 regions, which I did before, I could do the whole region from 0 to 4 of just the square root of x. Take that answer and subtract my area of that triangle, because it is a perfect problem. So that would be, the 1/2 times 2 times 2. So let's try that. That's going to give me x to the 3/2 divided by 3/2 from 0 to 4 minus the 2. Plug in the 4. We've done that number before already. If you plug a 4 there, the square root of 4 is 2. 2 to the third is 8. 8 times 2 is 16. 16/3 minus the 0 minus the 2. 16/3 minus 6/3. Lo and behold, 10/3. Wow, there's more than one way to skin a cat. I'm not going to do another one right now, but I would do this one. You know what? You should do this one. You know what? I'm going to have you submit this work in It's Learning Today. I will add that task since I'm probably not at school. So I will use horizontal rectangles. Right minus the left. That means you got to solve both of those for x. You're going to integrate from 1 to whatever that is. How do I, not 1, 0. Oh, he already told me it's a 1. But, well, how would I know? I would have to set these two functions equal to each other and see where they cross. And you'll get this ordered pair. But anyway, enough of that. Piecewise, if you wanted to find out the area bounded by this, you'd have to break it up into one piece, three pieces. And so you'd have to know what the equation of this curve is. You'd have to know the equation of this line is. And look at, they gave them to you. And you'd have to know the equation of this line is, which it's just y equals a -1 from 2 to 3. Okay. You're going to submit this one too. That takes me too. That's it. I'm probably going to cut back on some of these homework problems. So why don't you work on them, but I'm going to tell you which ones I'm going to cancel out. There's too many on that page. I could probably pick some. I mean, there's a lot. And you can kind of